In this section of the video, we go through our data cleaning process. We start first by importing the usual suspects: OS, RE, pandas, numpy, matplotlib, and all the tools we need for file handling, data manipulation, and plotting. We also silence minor warnings to keep things clean. Then there's a tiny installer function that ensures key libraries like pygenitor and shardata are available. Next, we define paths for the raw data, cleaned output, previews, visualizations. The script checks these directories exist or creates them if they don't. Then it lists all 69 target CSV file names that we'll process. A helper function, find target, scans the main directory and finds only the CSVs matching our target list. It prints how many files were found so we know what we're working with. The read CSV ultra function is a super resilient CSV reader. It tries multiple encoding separators and even raw text decoding to handle corrupt or non-standard files, making sure we get a usable data frame every time. Then we normalize the data, standardize province names, recognize month and year columns, replace weird none-like strings with a real none, coerce numeric looking strings into actual numbers, pick columns like municipality, province, and time automatically. The force keys function ensures every row has a municipality, province, and period column. If missing, it tries to infer them from column names, file names, or wide month formats. Unknown municipalities get special placeholder names. For each file, we create before and after visualizations, histograms of numeric columns, boxplot for value distribution, correlation heat maps. This helps quickly see what changed during the cleaning. Now, the core loop. Read CSV robustly, tidy column names and nans, force keys and periods, deduplicate globally and by key without losing more than 10% of rows, fill missing numeric values with median, saved clean CSV and preview snapshots, generalize or generate visualizations. Finally, the script saves a JSON audit of all cleaned files, tracking row counts, retention ratios, and key columns, and logs any errors. At the end, we print a summary of how many files were cleaned, errors, and where to find visualization. Moving on to the feature engineering pipeline, the code section in this notebook here generates event onset labels and lag features from multiple sources: AC LED protests, fatalities, crime, and census data. Key configs are label mode, onset or any, quiet window of 3 months, and horizons of 1, 3, 6 months. CSV data is loaded, keys are normalized, and datasets are merged. We aggregate protest counts, fatalities, crimes, and census metrics per municipality period. Temporal features include months since last protests, time index, month, year, fiscal quarters, and sinusoidal month encoding. Lag and rolling aggregates over 1, 3, and 6 months are computed. Labels are future event or onset event based on past quiet periods and upcoming activity. The feature matrix drops identifiers and targets, encodes categoricals, and fills missing values. The script outputs X and Y, fully processed for machine learning, with summary counts of positives and negatives. And now moving on to the training pipeline. It performs cross-validated logistic regression with automatic group selection, municipality, month, or plain straight field folds. We configure 3 folds, a random seed, and a decision threshold of 0.3. Helper functions safely compute metrics like AP, ROC, AUC, F1, precision, recall, accuracy, log loss, Breer score, and confusion matrices. Splits are generated via straight field group K fold if available. Otherwise, we fall back to greedy group balancing or plain straight field fold. For each fold, the training set is cleaned. INFS replaced with nans, all nans and zero variance columns removed. If a single class exists, predictions default to the prior probability, Otherwise, we apply a pipeline, median imputation, optional smooth for minority class, standard scaling, and logistic regression with balanced weights. Predictions are evaluated on the test set using all matrix and logged per fold. Finally, we summarize cross-validation results: mean AP, ROC AUC, F1, precision, recall, accuracy, log loss, Breyer score, and mean confusion matrix counts. As illustrated here, the results we attained are an ROC AUC of 1, a precision recall AUC of 0.962, and an F1 score of 0.994. In practice, this means 98.7% precision, almost no false alarms, and 100% recall, meaning we didn't miss a single protest event. In fact, only one false alarm was observed across more than 3,400 cases. This shows that our system is both highly reliable and actionable, giving decision makers a trustworthy early warning tool for service delivery protests. In this section of the video, we go through the full system architecture. This is a Flask-based web application that predicts service delivery protest risk at the municipality level in South Africa using machine learning models. It provides an interactive dashboard with risk visualization, explainable AI, and government reporting capabilities. The system architecture and components include a web application layer, machine learning pipeline, the data layer. Moving on to the machine learning layer or aspect of the project, we have the model service. Model service, its main purpose is that it is the core machine learning prediction engine. Its key features include a safe model loading with multiple fallback mechanisms, batch prediction processing, feature importance calculation, mock predictions when model is unavailable. Then we have the feature engineering, which purpose is to transform raw data into machine learning ready features. And its key features include temporal feature extraction, which is the month, year, fiscal quarters, lag, variables and rolling statistics, province encoding and categorical handling, risk score normalization. Then we now have the web application components, which include the dashboard routes, the main dashboard interactive choropleth map with a risk visualization, individual prediction, custom municipality risk assessment, batch upload, CSV processing for government users, download results, export predictions as a CSV. Moving on to API endpoints, we have API for the predict individual, where we have custom municipality predictions. Then we have the API for uploading a CSV for the batch processing. We also have the API endpoint for downloading the results, exporting the result as a CSV file. Right.